Hello everyone. In this video, I want to briefly talk about different probability distribution functions, which are continuous distributions, and then probability mass functions, which are for discrete distributions. I just want to show you the general formula for them, their parameters, and briefly talk about their applications. Now, each one of them needs at least one video of its own if you want to completely delve into it and talk about everything and applications and so on. That's not the goal of this video. This is an introduction, an overview of them very fast, but again, any of them that we seem useful and very applicable to engineering, we're going to go over them in future videos. So the first one that you know probably, or the first two that you have seen a lot, is one is uniform distribution, giving anybody and everybody the same chance, and then normal or bell-shaped distribution, which is this negative exponential. So if you look at the uniform distribution, then for any range, let's say for instance 0 to 1, which is like the rand command in MATLAB, when you call this rand command, it gives you a random number, right, between 0 and 1. Now, what is the chance that you end up with a 0.1 or a 0.5 or a 0.8 or 0.9 or any number? The chance for any of these numbers to be drawn out of that random number generator is the same. Now, does it mean that, for instance, if you run this command 1,000 times, and you create a plot, would you get a perfectly straight line like this? No. This is a theoretical one, okay? But you get relatively close to a line. So you might end up, I don't know, if you break down into 10 bins, for instance, this bin from 0.9 to 1, maybe you don't exactly get 100 data. Maybe you get, for instance, 98 data. Maybe here between 0.1 and 0.2, for instance, you get what? In this bin, you get, for instance, 102 data or something like that. But these numbers are very close. So the chance that the sample comes from any location within this range is almost the same. Okay, that is called uniform distribution. And in theory, when we look at it as a PDF, a probability density function, the amplitude of that should be 1 over b minus a, where b is the maximum of the range over which you take a sample and a is the minimum. For instance, if b in this case is 1 and a is 0, then magnitude is going to be 1 over 1 minus 0, which is 1, and that is what you can see over here. Okay? One important thing about any probability distribution function that I mentioned in one of my previous videos under engineering mathematics when I talked about probabilities is that the area under a PDF where it goes from negative infinity to positive infinity, it should be equal to 1. So integral of any probability distribution function over the entire possible range should be equal to 1. And for that reason, if this is from a to b, this amplitude here should be 1 over b minus a. So the area of this rectangle, which is b minus a times 1 over b minus a, becomes 1. Okay, so that is this uniform PDF probability distribution function. So the two parameters are only the range over which it is defined. It is used a lot in random sampling. As I said, if you want to give all points in the range the same chance of being picked, then use this uniform distribution. Now, if you want to know how a random number generator in MATLAB or any other software is working, I have a video under my playlist MATLAB. Let me show you. That's this one here. It's called Random Number Generation in MATLAB, RNG seed, and then this algorithm called the Mersenne twister. So here I talked a little bit about theory and some parameters for the random number generation in MATLAB. So if you want to know how you get a random number generator with the command rand, as I said in MATLAB, then you can go ahead and watch that video. So it is used a lot for simulations, Monte Carlo simulations, or anything that needs equal likelihood. When you don't have any preference for where the data is coming from, in which range, you want to give them all the same chance, equal likelihood, that is where you use this uniform distribution. The second one is normal distribution, which is given by two parameters, an average and a variance or standard deviation squared, mu and sigma. This is a bell-shaped curve, and the equation for it is 1 over 2 square root 2 pi sigma squared exponential of negative x minus average squared over 2 sigma squared, okay? And the plot of that is, of course, this famous bell shape here. This is the standard one for mu of 0 and sigma of 1. And you see the average is at 0. And then, as I said in one of my previous videos where I talked about normality of data, then as you get away from the average, the chance of being picked is dropping fast. It's an exponential of negative x squared, x minus average squared. So the chance of being picked when you're far away from the average is very, very small. And the chance of being picked when you are very close to the average is very high. Okay? So about 99.7% of the whole area, remember the whole area under the curve is 1. So about 0.997 is the area only between negative and positive 3 sigmas away from the average. In this case, where sigma is 1 and mu is 0, then between negative 3 and positive 3, which is mu plus 3 sigma and mu minus 3 sigma, this includes about 0.997% of the area under the curve. So if you want to use the command, any command that generates this kind of random number, in MATLAB that command is called randn. It generates random number from a normal distribution. The chance for you to end up with the number, if your mu is 0 and sigma is 1, the chance for you to end up with some number like 4 or negative 4, negative 5, 6, something like that, is way, way less than 1%. But if your number is the number that you want to get out of this command is close to 0, you have a much, much bigger chance, okay, about 0.4. Again, this amplitude here is corresponding to this guy over there, right? Because sigma is 1, so your maximum amplitude, which happens at x of mu, where this exponential is all 0, right? When x is mu, that whole thing is 1, so that is that amplitude. And when sigma is 1, that number is 1 over square root 2 pi. So this number that you see here, that is 1 over square root 2 pi, okay? And again, that number is there, that constant is there, such that when you integrate this from negative infinity to positive infinity, the integral becomes equal to 1. That's why you need to scale everything down. If it was just a negative exponential, the area will be more than 1. So you have to multiply by that constant to get it equal to 1. Now, where would you use this? In lots of places. One of my next videos is about CLT, or central limit theorem, which says that regardless of what kind of distribution your original data is coming from, if you look at the average of your samples and the number of data in your sample is not small, you make it bigger and bigger, then the distribution of the averages of these samples is going to be a normal distribution. And again, I'm going to show you in one of the future videos. In many measurement scenarios, in sensors and so on, where there are so many contributing factors and we don't know them very well, and these contributing factors can sometimes reinforce each other, can sometimes cancel each other, you'll see that if you look at the measurements, the errors in the measurements, the noise in the measurement is many times a normal distribution. distributions of many things like human height, human weight, many of the, especially human height, okay, the ones that are not affected so much by like our eating preferences or so on, those are a lot normal distributions. Okay, so for instance, in US, if they say the average height of a man is 6 feet, then you see a lot more men close to 6 feet than the men that are in 4 feet or 8 feet range. Okay, so if you look at the human height, it's mostly also a normal distribution. Of course, this average and this standard deviations, that depends from sample to sample, community to community. But this is one of the most common, if not the most common, distributions that you'll see all over the place. The next one we have is called exponential. Okay, clearly, as the name says, it is an exponential. The only parameter this guy has is a lambda, which is the rate of this exponential, of course. And if you want to look at how this one looks like, this is how it looks like. Clearly, it's not symmetric. As you get away from 0, it drops exponentially, very fast goes to 0. So depending on the lambda, this is for lambda of 1. After like 4 or 5 lambda, your chance is almost 0. Okay? And again, the whole area under the curve is, of course, 1, and that's why you added this lambda. So again, when you integrate this, the integral becomes basically equal to 1. That's why this lambda is added. Because when you integrate e to the negative lambda x, you get a 1 over lambda, and that with this one would cancel each other. Where would you use this? This is used in so many different places when you want to see how much time it takes for something to fail. For instance, like if you have electronics or something, right? And you want to know how much time it takes before some electronic fails, then you can use this kind of distribution. If you plot the time that it takes for some electronics to fail and do that for so many different electronics and plot these and look at their histogram, their basically distribution is going to be an exponential distribution. Okay. So there are other things too, like in Poisson processes, inter-arrival times, and so on. We'll get to that in probably one future video when we only talk about exponential one. The next one is called the gamma distribution. Gamma has 2 parameters, alpha and beta. If you look at it, it has 2 terms in it, a power term and an exponential term. The power term has power alpha in it, or alpha minus 1. The exponential has negative beta, and there is this constant here, okay? Beta to the alpha over gamma function of alpha. The reason we call it gamma function is also because of this gamma function of alpha, which is in the denominator. So beta determines the rate and alpha determines the shape. Again, this one can be used for queuing models, okay? For Bayesian priors, for waiting times, and so on. So this one is really used in queuing. Another thing you might want to talk about is about insurance claim. If you want to talk about, one second, if you want to model insurance claim, because nothing is perfectly deterministic, there is some randomness in it. If you want to look at modeling of insurance claims, and you can draw a probability function for that, or queuing times, then gamma is your function of choice. So let me briefly clarify a few things here. One was, as I said, there is this gamma function here, right, that you have. If you just forgot what gamma function was, gamma function is like a generalized, basically factorial function. So it is this function, gamma of z is integral from 0 to infinity of t to the z minus 1 e to the negative t dt, right? And then for an integer number, gamma of n is n minus 1 factorial. Okay, and if you look at this here, t to the z minus 1 e to the negative t, that's the same thing that you have over here. Look, that's the same thing. You have the power function to this guy, the shape minus 1 times exponential of negative other. So you see this form and this form, they are very similar and the same as gamma. That's why we call it the gamma function. That's one thing I need to clarify. Second thing, I said alpha is a shape factor and beta is a rate factor. So let me show you that as well. In this picture that I got from Wikipedia, you can see that here we have different curves, and these are the PDFs, by the way, PDF of x versus x. You see here that if you look at, for instance, let's say red versus purple, right? Or let's look at some of the things that are similar. So look at this. Look at these two, actually. Red versus orange. So both have the same beta, the same rate, but alpha of the first one is 1, the next one is 2. And if you look at the red versus the orange, you see that this one straightly goes down to 0, while this one starts from 0, go up, and then go back down. Okay, so it's alpha that determines for you whether you straightly go down or whether you first go up and then go down. And if you look, the two that have alphas that are straightly going down, the red and the purple, if you look at their alphas, they are at or less than 1. These other ones that they all first go up and then go down, if you look at their alphas, they are bigger than 1. So alpha, whether it's less than 1 or bigger than 1, that will determine what kind of shape you are getting. And then there is rate. So for instance, if you look at orange versus blue, right, this one and this one, you see that, or let me look at two of them that have similar alphas and different betas, so you can appreciate that better. But let's see. Yeah, there is not exactly any pair of them that have the same alpha but different beta, but you kind of see if I go down here, let's say from this one to this one, although the alphas are not exactly the same, but going 2 to 1, right? Look, you go from yellow to green. Look, it's the rate of decay. You see green is decaying faster than yellow does, okay? And also you can look at other ones. So this is the rate that they decay. That is different. Now, if you want, I have a code that I written and it can give you all of these different ones. Okay, so I can show you that. But what you can see is beta is why we call it rate, because it is this exponential term. So because the exponential term has bigger decay, bigger decrement than the increment of the power function. So the whole thing, when x goes to big numbers, drops to zero when x goes to infinity. But since this function grows a lot or goes down a lot faster than this one going up, then the overall drop rate is mostly determined by beta, but it's not completely independent from alpha too. So the fact that we just call beta the rate is not correct. Alpha also affects the rate, but not as much as beta does. But alpha, definitely the fact that it's bigger than 1 or less than 1, it will affect the shape. And you see why 1, because here alpha is subtracted from 1. So when alpha is bigger than 1, this power function has a positive power. When it's less than 1, it has a negative power. It goes to the denominator. Okay, so you see why the comparison of alpha is against 1, and beta here kind of have the effect of rate. And as I said, in insurance claims, if you look at insurance claims and the aggregate insurance claims, that's one of the places that you see the gamma function. In rainfall, there is another one. And also, if you have any process where the timing is determined by an exponential function, so if you have an event, right, of some, you have some process that has a bunch of events that has happened, that will happen, and the time that it takes for each one of them, these times coming from an exponential function, then the time you need for the nth event to happen, so let's say for instance n equals 4, the time you need for the nth event to happen, that is coming and as a gamma function, or will be basically described by a gamma function. Okay, so now we move on to the chi-squared function, this guy here, which is used a lot in statistics. The only parameter it has is this degree of freedom k. And if you look at it, it is actually quite a bit similar to the gamma function. It is an exponential and it is a power function, and there is this gamma here. Now, let me show you the shape of these, because I guess I missed to show you. So that is the gamma function. This is for alpha of 2 and beta of 1, right? But as I said, I written a code and I'm going to change it. So this time I'm going to change it to alpha of 2 and beta of 2, and we can compare it against this if you want to see how it looks like. So this is your gamma function. It is basically a skewed function to the left side. And chi-squared is also very similar. If you look at them, as I said, these two are quite a bit similar functions. And of course, the gamma function is a little bit more picked. This one is a little bit kind of flatter, but their behavior is very similar. In gamma function, you have two parameters to control the shape of it. Here you see alpha of 2, beta of 1. You have two parameters. Okay, but here you only have one simple k. So alpha and beta in this case are both functions of k, right? Or actually in this case, beta is constant really. If you compare it against that, you see beta is like 1/2. And alpha here is basically like k over 2. Okay, so you see it only changes alpha here really. Beta is like a constant. It only has one parameter to change as opposed to two. This is really useful in lots of different things in statistics, from hypothesis testing, from variance estimation, from quantiles, and lots of other things that you want to do. This confidence intervals, right? So when we say variance estimation, one of the things that we do for it is confidence intervals. I will have a separate video for this. And by the way, before we move on, these are different shapes of the chi-square distribution for different k values. So you see for k of 1, it's just direct drop. For k of 2, again, direct drop, but slower. And then after some k, you see now it is going up and then going down, okay? So this is the effect of k on the chi-square distribution. Then we have 3 more continuous PDFs to talk about. The next one is called the Weibull distribution. Lots of applications in engineering, from reliability analysis and fatigue. Okay, and again, probably I have to make a video about this alone, because this is very useful in engineering. If you look at this, again, it's similar to the two previous functions. It is a power function and an exponential function, while this time the k provides basically the shape and the rate, and you can scale the x by dividing it by lambda, so lambda is your scale factor. Okay, so if you look at the shape of Weibull, of course, it should be similar to the two previous ones, you see, but again, this one similar to the gamma function. It has two parameters that you can control, and here are the effect of them. You can see here, these are different lambdas and different k's, right? So you see they're all drawn for the same lambda, but for different k's, and of course you can change lambda as well, and lambda would scale the whole x-axis, okay? So, and I can show you that as well. So as I said, here I have two pieces of code. The first one is, if you run this, it is going to plot all of these different continuous and the next set of discrete functions. It plots not only their probability distribution function, it also plots for you the cumulative distribution function. And then for discrete ones, it plots the probability mass functions and the cumulative mass functions. Okay, so by one click on this, it gives you all of these functions. So look here. So this is like the y-bool. This is the CDF of y-bool. This is chi-square CDF of chi-square. This is the uniform. This is the CDF of uniform. And their PDF. So PDF on the left, CDF on the right for the same set of parameters, but you can go ahead and change any of their parameters. And these are the discrete ones that we're going to see, of course. Okay, these are 6 discrete functions and 8 continuous ones. So these are, again, all of the discrete ones. And again, these are the parameters in them. So if you want to go and change something, you can do it here. But to give you a better option, I also have developed this app here, which is even better. So if you click on this, now you can do it one at a time. So you go and say whether you want continuous functions or discrete functions. If you want continuous, then it allows you to pick any of these 8 functions here. And if you want discrete, again, you can pick any of these discrete functions here. And then here you can provide the parameters, right? So let's say I want to go to continuous and I want to, let's say I want a gamma function, right? And here, by the way, k and theta is shown, but you can call them alpha and beta, okay? So I can change that if you want. Or I want a normal distribution, so a mu and a sigma, and then you say plot, and boom, that's your PDF and CDF, right? Or if you go to discrete, right, and say I want the binomial with n of 10 and p of 0.5, there we go. You get your PMF and you get your CMF. Okay, so here you can literally plot any function with any set of parameters. So these two combined can give you lots of information. And of course, I'm going to give you access to both of them under video description. So you can do that. So anyways, this is your y-bool distribution with 2 parameters, lambda and k. Okay, very similar to the 2 other ones, but of course, different applications. As I said, it needs a video of its own to talk about how you use it for reliability and fatigue. The last 2 functions in the continuous that we want to talk about, one is the Cauchy function, which, as you can see, this is basically like a hyperbolic function, right? There is only a denominator here. There is x0, which determines the location, and there is a gamma for scale. This is again, it needs a video of its own, but it is good for outlier modeling and for resonance behaviors. Okay, so it can be used in those kind of applications. If you look at the shape of this, now you see this is kind of similar to a normal distribution. Okay, this is a symmetric distribution. X0 here is the center, which in this case is 0. This 1 determines the spread in this case, right? But you see, it's different than the sigma that you had in a normal distribution. Okay, but clearly that gamma parameter here will determine the spread of the function, but it's kind of, as I said, acting similar to the sigma, and x0 is acting similar to the mu. Okay, so this is this function here, and if you want to see effect of them, here is one such plot. So look, these are all for x0 of 0 and different gammas. Look at that. You see that when your gamma is smaller, you get more of a picked kind of sharp, a bigger kurtosis. And then the further flat it goes, the gamma drops. So bigger gamma means smaller kurtosis. And then if you change x0, of course, you can shift it to the left and to the right. In general, it has a bigger kurtosis compared to a normal distribution. And of course, you know, in vibrations and whenever you have a resonance, this is the kind of thing that you have, right? You see at some specific location, which you call natural frequency, which in this case, the x0, you're going to see some sharp amount of resonance. And that amount of resonance, or the resonance magnitude, so this is like your omega n, and this is like your resonance magnitude mr. Okay, that gamma determines that. So it is really useful for basically resonance behavior. And finally, we have a log normal. So a log normal, if you look at it, it is actually very, very similar to the normal distribution. Because if you look at this, I mean, this is very similar to the normal distribution with some differences. What are they? First of all, here instead of x is natural log of x. Also, the x here appears in the denominator. In normal distribution, that was all a constant. But here, x appears here, and here you have a natural log. So that's why we call it log normal. And this is mostly used in finances and in processes that they are called multiplicative. Again, what are these different processes? Poisson process, multiplicative, all sorts of things. I don't want to get into them right now, but know that this guy has applications in finance, and similar to a normal distribution, of course, mu and sigma are the two parameters. Now, look at the interesting thing about this. This guy is not symmetric. The normal distribution is symmetric about mu. This one is not. Okay, that is the beauty of this, that log normal is a skewed version of normal distribution. It's not symmetric. And here you can see some effect, right? So this is mu of 0. This is mu of 0. Look, they both have mu of 0. This is sigma of 0.25. This is sigma of 1. So even sigma can change the location of the mode. Not only the shape, also the location of the mode. This is also mu of 0, but sigma of 0.5. Do you see how it behaves? So this is like 1, this is 0.5, this is 0.25. So it seems like the bigger this, the smaller the sigma, the further the mode moves to the right side, okay? And of course the shape also changes. And seems like the smaller the sigma is, it is kind of getting more symmetric. The bigger the sigma is, it is further skewed to the left. Okay, so this is also an interesting distribution that we can plot here. And by the way, I went into the app and changed that. So now for gamma is alpha and beta. So here are those 8 PDFs that we talked about and their corresponding CDF. And then similarly, we have the discrete ones that I'm going to talk about them. There are 6 discretes that I included here. So let's fast go over the discrete ones. So the first one is called the Bernoulli, which is a special case of the binomial distribution. So for that reason, let me talk about binomial and then come back to Bernoulli. So if I make n equal to 1, binomial becomes Bernoulli. So binomial is when you have a random phenomenon, random event, something that has a chance of success of p, where p is less than 1 between the 0 and 1. And you repeat that n times, and you want to know k successes out of basically n tries. So let's say you flip a coin, and it has like half 0.5% for head, 0.5% chance, 0.5, not percent, 0.5 for tail, and you threw it 10 times, and you want to know what is the chance of ending up 3 times head and 7 times tail, right? Then you have those 3 and 7 here, and p is the chance of success, 1 minus p is the chance of failure, and these are all different combinations. So that kind of phenomenon in general is a binomial distribution. It has 2 parameters, n and p. N is the number of trials, and p is the chance of success. In engineering, we use it for quality control and for when the outcomes are binary. So it's either failure or success, it's head or tail. It's basically working or not working, anything like that. When the phenomenon are binary, only 2 outcomes possible, then we can look at that. And that's another reason for quality control, that this one can pass the quality test or cannot pass the quality test. Okay, so these are in general binomial distributions. And the shape of that, if you want to look at it, is right up here. This is for n of 10 and p of 0.5. You see it's symmetric, right, in this case. And this is let me see this one here. These are the effect of the parameters. So you see that the shape is symmetric, but depending on the P and N, you get different results. So for instance, if you compare blue and red, they both share the same P, but different N's, okay? And you see when N gets bigger, the mode kind of drops, right? And you shift to the right. And here you see the blue and green for the same N different P's. And when P gets bigger, of course, it will be shifted further to the right, okay? So P and N both have effect on the location of the center and the sharpness of the distribution. And when N becomes 1, when you only try that one time, not N times, you just try it one time, then that's called Bernoulli. So in Bernoulli, you only have one combination, so this guy goes away, and this X here that you have can only be 0 or 1. So it's a single success or failure, not a bunch of times. In quality control, when we want to check whether something is passing quality or not, we do not suffice to just test one sample out of our production line or conveyor. We look at a bunch of them. So typically we use binomial, we barely use Bernoulli. And then now that we just talked about it, and this is Bernoulli, of course, right? This is for like 0.7 and 0.3. Okay, so you can see that here. Now, there is another version of this that is called multinomial. Let me just mention that briefly. So this is like a generalized binomial. So this is good when you don't have only two outcomes. You can have several discrete outcomes, okay? Like for instance, if you throw a dice, you don't only have 0 or 1, you have 1 all the way to 6. If you have surveys and like a Likert scale, you have 5 different outcomes: strongly agree, strongly disagree, neutral, stuff like that, right? So when you have different discrete number of outcomes, and these outcomes could be x1 all the way to xk, and their chances of success are p1 to pk, okay? And then you want to know what's the chance that P1 or X1, P1, the one that has chance of P1 happens only X1 times, the one that has chance of PK happens XK times, and so on. Well, of course, some of these P's should be equal to 1, and some of the X's should be equal to N, and these PI's are all between 0 and 1. Then you use this multinomial. Okay, so this is good for where you have several outcomes. Okay, so your test can succeed or it can fail, or maybe no general conclusion can be drawn. Then you have 3 outcomes. Now you have to use this one. Okay, so geometric. Geometric, if you look at it, it basically only has one parameter P, which is between 0 and 1. And for x happening k times, the formula is 1 minus p to the k minus 1 times p. And this is when you repeat some trials of some experiment back to back, and you want to know when the first success happens. Okay, so when you want to know when the first success happens and look at the distribution of that, that is a geometric distribution. And let's see, I should have something from that. Yeah, there we go. So these are for different P's. Okay, and you see that when P is large, right, you have this sharp drop. As the number for X get bigger, and when P goes down a little bit, you still have the drop, but is not as sharp here. Okay, so if I want to explain that in another way, I can say that this probability gives this distribution, this probability distribution, this PDF gives the probability of first success requiring k trials. In this case, X is representing that k. So if you want the first success to happen after 2 tries, 3 tries, or 6 tries or 10 tries, the chance of that drops fast, right? Because if the first success happens after 2 tries, or if it happens after 10 tries, the fact that you need to do 10 tries to get the first success is less than you just need to do 2 tries and get the same success. Now, of course, that depends on how much success you have for 1 try in the first place, right? But the more that you try, the more trials that you have, the better chance you have to get 1 success. So it's very rare that you need to try that test 10 times before you get 1 success. That is highly unlikely. Okay, let's say P of 0.5, which is throwing a dice. So if how many times would you see that you need to throw a coin 10 times before only the first, let's say, head shows up? Well, most of the time, the first 2 that you try, probably one of them is a head. So the fact that you need to try 10 times, all the 9 previous times were tails, and this last one is only head, right? That is much less. That goes down geometrically, and that's why you see this sharp drop, of course. Okay, when we go to the next one, it is the Poisson distribution. And for Poisson distribution, if you look at it, the K parameter here shows as a power function and a factorial. And the parameter here is lambda, which determines the rate. And basically, it counts the events per interval. Like what? Like how many calls you might get in 1 hour. So what does that mean? Let's say, for instance, the chance that on average in a day you receive an advertising scam call or something like that is like 2 times a day. So on average, your phone rings 2 times a day and you receive a scamming or advertising call. Now, what's the chance that today your phone receives 5 advertising calls or receives 0 advertising calls? That is your K, right? Which is different than lambda in general. And lambda is that average. So lambda is that average rate that you expect, and K is anything equal to lambda or different than lambda. That's the chance of that happening. Okay, and you can show that this is coming from this Poisson distribution. So if you want to count events per interval, right, then this is one good thing, right? For instance, if you receive a GPS update once every minute, like, is there a chance that, of course, if it's a random thing, because GPSs are not super random, but what is the chance that you get a GPS update after 58 seconds or 1.2 minutes or something like that, correct? As long as those phenomena are random, because again, GPS is mostly deterministic. There is some randomness to it, but it's not too much. But if there is anything that is random, then you can consider the chance of events per time by a Poisson distribution. And if you look at that, so this was the geometric one, the previous one that we saw, and this is the Poisson, okay? So of course it's not continuous, it's a mass function, so it's a discrete one, but this is for lambda of 3. You see that 1, 2, 3, you see the highest chance of happening is equal to the average, of course. If the average is 3, the biggest chance that you can get 3 calls per minute or per day is exactly 3. The further away you move from this average, your chance drops big time. So the chance that you get what? You get, for instance, 7 calls on that day is way less than 2, because 2 and 3 are very close. But you see, 5 is much less than 3, 7 is less, and 10 is like almost close to 0. So stuff that are further away from the average rate are not happening with too much chance. Okay? Now, 3 other to go. Now, the next one is called negative binomial. Okay. And if you look at it and compare it to binomial, you see that it's kind of similar or related to that, right? So let's take a look here. You see, they both have this kind of combination term, them. They both have a success rate P. Now, as opposed to this one that had K and N, this one has R and K, where R is the number of successes that is fixed, and K is the count that you want to know. Count of what? We'll see. In here, N, the number of total trials is fixed, and again, K is the number of successes. Okay, so what is the difference? The difference is this. In binomial, we basically fix the number of trials. So let's say we want to throw a coin 10 times with the chance of a head of P and a tail of 1 minus P, and we want to know exactly how many, basically, if we wanted 3 heads and 7 tails, what's the chance of that, correct? So here in the binomial, N is fixed. And what we want to do is to count the number of successes. Or if we know the number of successes, what's the chance of that? In the negative binomial, on the other hand, R, the number of successes, is fixed. So you want to count what? You want to count the number of failures before reaching our successes. Okay, so here the number of successes is fixed. You want to know the number of failures, the chance of failures here. Okay, K represents that. That's why we call it negative binomial, and it can be used in lots of different applications, right? And you can imagine that's the same thing. If you have a phenomenon that has only a binary chance, right? It's either happening or not happening with the chance of P and 1 minus P. And you want to know the number of failures that you need to have before our successes would happen, then this is your model, right? So how many times do I need to, for instance, test this circuit? How many failures would I see before I get 3 successes? Before 3 times this circuit works properly, how many failures would I see? That is a negative binomial. And of course, as I said, the parameters are R and P. And let's see if I have a plot for that. There we go. So this is R of 5 and P of 4. And again, if you compare it against the binomial, you see how it looks like. And this one was symmetric. This one is not really that symmetric. Okay. And let's see, do I have a plot of that here? No, but if you want, I can use my application here and show you what happens when R or P are changing, right? So this is my application. I can go to discrete and go to negative binomial. So this is R of 5 and 0.4, right? Right, let's see. Which numbers did we use here in this plot? Yes, 5 and 0.4. So that is how it looks like, right? And then now I change, for instance, this R of 5 to R of 1 or R of 2. You see? Okay, so that is 2. That one from another plot. Let me do to 4. Okay, you see how it works? Make it 6. Then change the P now, so make it like 0.7. Okay, make it 0.8, and so on and so forth. And this is the effect of R and P. This is the PDF, PFMF, this is the CMF, but these are the kind of behavior that you would see. Finally, by the way, this geometric distribution is a special case of negative binomial. Okay, so remember that Bernoulli is a special case of binomial. Geometric is also a special case of negative binomial. We also have discrete uniform, right? So you have n number of discrete phenomenon, and they are completely independent from each other, like when you roll a dice or you have a random selection. Again, those things have to be completely independent from each other. Then the chance of each one is exactly 1 over n if there are n possible outcomes. Okay, like for a dice is 1 over 6. And then finally hypergeometric, which is just coming from a bunch of basically combinations. So you have 3 sets of combinations here. It has 3 parameters, the population, and here is the sample size, so really 2 parameters, but k is the number of success items and n is the population. And this is when you do sampling without replacement. And you know that, correct? When you take a sample out of something and don't replace it, and then from the remaining again you take a sample, then this hypergeometric can model that. And let's see if I have one for that here. I don't see it. This is the discrete one, of course, for 6 possible outcomes. Let's see if I have something here. There we go. So this is the hypergeometric. And basically this is the n of 500, k of 50, and then n of 500, k of 60, n of 500, k of 70. And you see that the bigger the k, you further shift to the right. And actually you do need n as your third parameter. So it actually has 3 parameters here. Okay, and so this is your hyper basically geometric distribution. So in this application that I have 6 of them. So if you go to discrete, I have the hypergeometric, but with only m and n, but you can add n as a third parameter if you want. Okay, so this is with the default n, but if you want, you can change that. And that's probably what I will do for you before publishing this. I will add a third option for n. And then I'm going to give you those, the corrected one here, okay? Something like that. So hopefully you got some initial idea of different PDFs and PMFs, and of course, they're cumulative ones that I just showed you. We just mostly talked about the PDFs and PMFs. Discrete and continuous, their formulas, how they look like, brief about their applications. As I said, many of them, they need a video of their own just to explain them. And I'll do that in one of my future videos. So thank you so much, and I'll see you in the next lecture. Thank you.